Yeah, hello everyone. I hope you can hear me. Could somebody unmute and tell me if you can hear me?
I can hear you, Joseph.
Yeah, thank you very much. Yeah, I am recording the lecture, and then the recorded lecture will be posted on eClass this afternoon. So it's almost time to start. It's 11:29. So I will be probably starting maybe a minute earlier than usual. So today's lecture will be devoted to interaction between charges, and to a large degree, this lecture will be a review of what you know from Physics 1801. But I decided to spend a little bit of time to review the concept of Coulomb's law, because it's so very important to understand it very well. So as you know, two charges either attract or repel one another. So like in this situation, we have positive Q1 and negative Q2. So these two unlike charges, positive and negative, attract one another. And these two forces, blue vectors, these two forces are of equal magnitude. And as you see, the direction of these forces is along the line connecting these two charges. But forces are the same, because magnitude of the force is given by this expression, which we call Coulomb's law. And the force depends on the product of both charges, Q1 and Q2. So even if Q1 is not equal to Q2, these two forces are of the same magnitude. Of course, these two forces are action-reaction forces. And by Newton's third law, if Q1 is attracting Q2, Q2 must attract Q1 with the same magnitude of the force. So the forces are of the same magnitude along the line connecting these two charges. And if the charges are of the same type, let's say two positive, then they repel one another. And again, these two forces, magnitude of the forces given by Coulomb's law, and the direction of these two forces, you see, is along the line connecting these two charges. And the force depends, as you see, inversely to the square of the distance between these charges. And I assume that these charges are point charges, which means the size of the charge is negligible. But the Coulomb's law is also valid for spherical charges. So if the charge would be located in the volume of the sphere, or uniformly distributed in the sphere, or on the surface of the sphere, then we can still use the Coulomb's law, but then the distance r is from the center of the sphere to center of the sphere. It is actually not completely obvious that we can use Coulomb's law for the sphere, because you see, let's say if I have two spheres like this, one here and one here, and if the charge is distributed on that surface, let's say, of the sphere, let's say uniformly distributed positive charge on the sphere, then of course we would have to take into account repulsion between each of these two charges. So let's say this charge acts on this one, this acts also on this one acts on all charges on that sphere. So it is not a trivial actually thing to prove that if the charge is spherically distributed, we can use the Coulomb's law, where Q1, Q2 would be the total charge on this sphere and on this sphere, Q1 and Q2, and distance would be from the center of the sphere to the center of the sphere. So to prove it, that requires integration, and maybe I will prove it in one of the future lectures. But yes, if the charge is spherically distributed, you can treat all that charge on the sphere as if it is located at the center of the sphere. And then the distance r is from the center of the sphere to the center of the sphere. So again, it's not a trivial thing to understand that we can use Coulomb's law if the charge is distributed in the sphere or on the surface of the sphere. So please remember that, yes, we can use the Coulomb's law even if the charges are not point charges, but they have to be spherical. But if the charge has not spherical distribution, let's say if the charge is on the long rod, on certain surface, then of course you will have to do integration, and the the objective of today's lecture is actually to do calculations when the charge is distributed on different objects with not on the sphere, but on any shape of the object. And that constant epsilon zero here is called permittivity of free space. And I'm sure you remember it from physics 1801, but quite often that constant 1/4 pi epsilon zero we designate by letter K, and that K is called Coulomb constant, which is equal 9 times 10 to 9 newtons meter squared per Coulomb square. So that much, of course, I hope you remember from previous courses. So any questions before I continue? You can unmute yourself and ask questions. But so that was a review. Now, the next slide you should also remember from physics 1801 that quite often we have to calculate the force on certain charge due to many charges. Like in this situation, let's say if we want to calculate force on that charge, positive charge designated Q0, due to charges Q1, Q2, and Q3, we have to use superposition principle, which means that we have to calculate the force acting on Q0 due to Q1, and that force is in this direction, F1, blue, because Q1 is negative, so it attracts positive Q0. So that blue F1 in this direction. Then Q2 is repelling Q0 because both are positive. That's the red vector, F2. And at the same time, Q3, which is positive, repels Q0 in this direction, F3. And the total force acting on Q0 is the vector sum of F1, F2, and F3. So you have to add these three vectors, and normally you do it by decomposing F1 into X and Y components, the same with F2 and F3, and then you deal with components, as you will see on the next slide. So we use superposition principle. Of course, it should be clear that now there is also force acting on Q1 because Q0 is attracting Q1. Q1 is repelled by Q2, attracted by Q2. Q1 is also attracted by Q3, right? So there are three forces acting on Q1. Of course, there are three forces acting on Q2 because Q2 is repelled by Q0, Q2 is attracted by Q1, Q2 is repelled by Q3, which is positive. So on each of these charges, there are now three forces in action. But in this now slide, I'm just calculating the force acting on Q0. So the superposition principle is very important, and that's what we will be using many, many times in physics 2020. So any questions regarding superposition principle? Yeah, I hope that is clear. And this is the example which was done in physics 1801, or it was maybe questioned on the test or exam, where here I included this slide just to give you a specific example how to use superposition principle, that if we want to find the force acting on 8 microcoulombs due to 6 microcoulombs and due to 4 microcoulombs, as you see, all three charges are positive. And the dimensions are provided. So this is 6 meters, this is 6 meters, this is also 6 meters. So yeah, so there's a lot of symmetry here. So what we have to do to find the total force acting on 8 microcoulomb charge, we have to find the force on 8 microcoulomb due to 6 microcoulombs using Coulomb's law. So K, Q1, 6 microcoulombs times 8 microcoulombs divided by square of the distance. And square of the distance, now this hypotenuse of the triangle would be, of course, by Pythagorean theorem, 6 squared plus 6 squared. That will give me the magnitude of F1. In the same way, I find magnitude of F2, which is this force due to 4 microcoulombs. So here we have 4 microcoulombs, 8 microcoulombs, and square of the distance times the constant. And then I decompose. You see, F1 is in this direction. So I decompose F1 into X component and Y component. Y component is negative because it is pointing down, and I took Y axis vertically up. And the angle is 45 degrees because, like this is like half of the square, right? So this angle and this angle are 45 degrees. And the same, F2, I decompose into X component and Y components. Both components are positive. Then I found the total X component, found the total resultant Y component. Once I have the X component of that resultant force and Y component of the resultant force, I can find the magnitude of the resultant force, which is in this direction. You see here that this would be the resultant force, which is, of course, by Pythagorean theorem, square root of X squared plus Y squared components. And then if necessary, I could find that angle, the direction of that resultant force with X direction using tangent function. So I did go through this example very, very fast because we did practice these type of questions in Physics 1801 and spent a lot of time on it. But I included this slide so that all of you, all students in Physics 2020 must know how to use superposition principle. So please redo this question on your own at home, redo it, cover the solution, redo it on your own. And if you do it correctly, that would be a good sign that you understand how to use superposition principle. So I understand that I did it very quickly, and probably you could not follow my calculations. I want you to do calculations at home. I just explained very briefly that, yes, I did use superposition principle. So any questions? Yeah, I expect that was all well understood in Physics 1801. So I hope that everyone, all of you, understand this very well. But the true purpose of this lecture today is not to deal with these point charges or spherical charges, but with continuous charge distribution. Before we do some more specific examples about charges which are distributed on some objects, I want to define linear charge density, surface charge density, and volume charge density. That was also done in Physics 1801, but this is now very crucial for Physics 2020. So please make sure that you understand what we mean by the charge density, linear charge density. So imagine that we have a charge uniformly distributed on a very thin rod. So let's say this is positive charge. So I draw that this charge is positive and uniformly distributed. Uniformly distributed means that there is the same amount of charge per unit length. Okay, so when the charge is distributed on that, let's say, very thin rod, you cannot just use Coulomb's law. For example, if you would like to calculate what is the force acting on this point charge, positive Q, let's say Q0, you cannot just use Coulomb's law, because you see this rod is not a point charge. The charge is distributed in space, right, on that rod. So we have to use some other approach. And the other approach is to divide the rod into that very thin rod into many small elements or small chunks. And one of these chunks here is designated, the length of that chunk is designated dl, like differential length dl. And the amount of this little element we will designate by letter dq, letter dq. And if that little chunk, that length dl is very small, approaching zero, then this charge on that little element, this little element, we can treat as a point charge. Remember, if you have questions, you can unmute yourself and ask questions instead of writing like on chat question. I prefer that you unmute yourself and ask questions right away. So we will have to divide that rod into tiny elements so that each element can be treated as a point charge. And then we can find the force exerted by Q0 by that one element. Let's say that would be the force, which here would be called maybe dF, differential force dF, tiny force. And then, of course, I would have to divide that rod into many tiny elements, like this little element, a little tiny element, and find the force due to each element of that rod acting on Q0, and use superposition principle to find the total force. So the question is now quite complicated. We did this type of question in Physics 1801, and many students understood that perfectly well, but not all students understood that very well. So yeah, we will have to deal with this kind of distribution of charge on the rod, and for that reason, we will have to define that linear charge density, and that linear charge density we will designate like in the textbook by letter lambda. So what is lambda? Lambda is amount of charge on 1 meter of length of that rod. So if the rod would be very long, how much charge is on 1 meter of it? On 1 meter. So that is the simple lambda. Lambda is the charge, amount of charge on 1 meter of that rod. Okay, so the unit of lambda is coulomb per meter. Coulomb is the unit of charge, meter is unit of length. 1 coulomb per 1 meter. That's the unit of lambda. But as I was explaining to you, we will have to divide the rod into many little tiny elements, many little chunks, and we will have to find what is the amount of charge dq on that tiny element of length, of that differential length dl. And to find that dq, we can use this type of proportion. So please make sure that you understand this proportion. So what this proportion is telling is this, that if lambda is amount of charge on 1 meter of length, so lambda is amount of charge on 1 meter of length, then the amount of charge dq on the length dl must be in the same proportion, which means dq to dl must be in the same proportion as lambda to 1 meter of length. And that proportion, yeah, if you're very good, I allow you to ask questions, but remember that this type of proportion will be only valid if the charge is uniformly distributed on the rod, okay? So then from this proportion, before you ask your questions, you see that dq, when you cross multiply, then dq is equal lambda times dl divided by 1. So lambda times dl divided by 1. But lambda dl divided by 1 is lambda dl. So that dq is equal lambda times dl. So if you know lambda, if lambda would be given, then you can express dq or as this product, lambda dl. So now your question.
So the SI units for dq dl will be coulomb per meter squared.
As well, yes. So unit of dq over dl will be coulomb per meter, because unit of charge is coulomb and unit of length dl is meter. That's correct.
No, because the unit for linear density is coulomb per meter.
Yes.
Right?
Yes.
So coulomb per meter over meter will be coulomb per meter squared.
Yeah, well, so let us clarify this well, maybe slightly more precisely. So yes, so first of all, unit of lambda is definitely coulomb per meter, and that lambda we call linear charge density. I did not write that, I regret that, but lambda is called linear charge density. So instead of here distribution, if you write linear charge density, right? Density because it is amount of charge per unit of length, and unit of length is 1 meter, right, in SI units. So lambda has unit coulomb per meter, and of course that ratio dq over dl is also unit coulomb per meter, right? So here I'm using proportion. Remember, this is just to write the proportion that dq is equal lambda times dl. And as you see, if lambda is in coulombs per meter, and here the product times dl, which is also in units of meter, then meter will cancel, and dq you will get in coulombs as required, right? So lambda is in coulomb per meter, dq, differential amount of charge, dq is in coulombs, and dl is in meters. because lambda is in coulomb per meter. That's the unit of lambda.
Okay. Okay, thank you.
Yeah. So remember that lambda is called linear charge density. Any additional questions?
Yes, sir. So we are assuming that dq is a charge technically, right? So that when we're calculating the force, we are, if we're calculating the force, we are, multiplying q0 with dq. Am I right?
Exactly. That's very correct. So if I would have, let's say here, that charge like previously, what you did say is very correct. I'm just try to clarify a little bit more. So yeah, if this would be Q0 and I want to find the total charge acting on Q0 due to entire rod, then first you would calculate what is the force acting on Q0 due to that one element on which charge is dq. That force would be in this direction, right? If this charge is positive on the rod, and that force dF, that tiny force, amount of force dF, would be written like you say, dF would be equal, the amount of force exerted by that one element on which charge is dq would be equal that Coulomb constant K times Q0 times dq divided by square of the distance, this distance. This would be distance r, and I have to write square of that distance. So this would be the force acting on Q0 only due to one element. Then you would have to take another element and find the force, which would be in different direction, and say this element would exert the force in this direction. So we would have to now find the sum of all these tiny contributions due to each element by using superposition principle. But you are right, that was your comment. dq, instead of dq, you would substitute lambda times dl. Here you would make that substitution. Instead of dq with lambda dl, and then you will see on the future slides, because we will be doing quite a few examples with that continuous charge distribution, and then you will progress now and deal with appropriate variables. But yes, you are right. dq you would replace by lambda dl.
Okay, thank you.
Yeah, you're welcome. Any additional questions or comments? Yeah, if not, then we will be also dealing with charge distributed on the surface, on different surfaces. So here, for example, you have a surface, and the charge, maybe positive or negative, is uniformly distributed on the surface. Maybe in the future cases, you will see that might be maybe a sheet of plastic with embedded charge in it, or maybe metal surface with the charge deposited on the surface of the metal. So in these cases, the charge is distributed, and in that case, it is convenient to define the surface charge density. Okay, density. So surface charge density, which we normally designate by letter sigma. So sigma will be amount of charge per 1 meter square of that surface. So how much charge is on 1 meter square? That will be meaning of sigma. And as you sigma will have unit then Coulomb per meter square. And we call that sigma surface charge density. And again, when doing calculations, we will have to divide that surface into tiny elements. So here you see one element, dA. dA is little part of that surface, differential area of that surface, dA. dA should approach 0, right? It should be as tiny as possible, but it's a tiny element of the surface. And the amount of charge on that area dA, we will designate by letter dq, by differential amount of charge dq. So as you will see in the future, we will have to divide that surface into these tiny elements, and one element dA is designated. So we will have to then find how much, if sigma is given, if the charge density is given, how much charge is per 1 meter square, then we will have to find how much charge is on that area dA. So what is that dq? And you can also find this from this proportion, that if sigma is the amount of charge on 1 meter square, then the amount of charge dq on area dA would have to be dq divided by dA, because dq is the amount of charge on that tiny area dA divided by dA. And this proportion is true if the distribution of the charge on that surface is uniform. And in most cases, we will deal with these cases when distribution of charge is uniform on that surface. So from that, you see, so amount of charge sigma on 1 meter square must be in the same proportion as amount of charge dq to the area dA. And from that proportion, you can write that dq can be written as sigma times dA. Right? So again, because sigma has units coulomb per meter square, dA has area, which is area in meter square, then dq will be in coulombs. So this expression we will be using very often. So this for linear charge distribution, and this is for surface charge distribution. So any questions about that surface charge density sigma?
Professor, so when do you need to, like, for example, do a linear charge distribution to calculate that? Because, for example, if you're trying to find the charge through, say, a copper wire, right?
Yes.
Do you use linear distribution, or would you want to go for, say, volume of the entire, like, thickness of the copper wire itself?
Yeah, that's a very good question, because actually we will be dealing with situation when the charge is on a very thin copper wire, let's say, right? So that would be a good example when we have and when we will deal with that linear charge distribution. But like you've mentioned, every wire has really certain volume, right? It's like little cylinder, very long cylinder. So you will see later on that charge on metal wire is actually distributed on the surface, not in the volume, but on the surface of that wire, on that surface. And the reason for that I will be explaining in the future lectures. And then even if the wire has little thickness and little diameter, but we can still treat that wire as very long wire. And then we will be dealing with that lambda. So lambda will be amount of charge per 1 meter of length of that wire. Okay, and that will be true because if the wire is now very thin, then we use that linear charge distribution, not volume charge distribution, for these two reasons, that the charge will be actually distributed on the surface, not in the volume, and although the charge will be distributed on the surface of the wire, but if the wire is very thin, then what will really count, as you will see in the future, is how much charge is per unit length, per 1 meter. So yeah, for this situation, we'll be using linear charge distribution. But when we deal, let's say, with metal plates, like in the capacitors, for example, then we will have to deal with that surface charge distribution. But there will be also situations when we will have to deal with volume of charge. So imagine that you have certain volume, maybe, let's say, volume of plastic in which the charge is embedded, let's say, because if the why I emphasize plastic, not metal, because if you would have the volume of metal, then the charge will be actually now distributed, as you see in most cases, on the surface especially in static equilibrium, on the surface of the metal. But imagine that we have volume of charge, maybe charge embedded in piece of plastic, let's say. So that would be a volume of charge. Then in these cases, we defined volume charge density. Volume charge density. And that volume charge density, we designate by letter rho, Greek letter rho. That's the standard symbol. So that volume charge density rho is just amount of charge contained in 1 meter cube of that plastic, let's say, in 1 meter cube. So the unit of rho would be coulomb per meter cube. And if the charge is uniformly distributed, then I can write this proportion, that rho with this amount of charge in 1 meter cube must be in the same proportion as dq over dv, where here you see little volume, dv, differential volume, which volume that dv should approach 0, and the amount of charge on that little volume we designate dq. So dq is amount of charge in that volume dv. Then dq to dv must be in the same proportion as rho to 1 meter cube. And then from this proportion, as you see, dq is equal rho times dv. So if rho is coulomb per meter cube, dv is meter cube, then dq will be in coulombs. So we will be using this relation also in the future. Okay, so so don't try to memorize anything. Remember these three expressions which I'm explaining right now on this slide, I will be using many times, and I will be now explaining again and again why these equations are correct, that dq is equal lambda times dl, for example. So any questions about this linear charge density or volume charge density or surface charge density?
Yes, Professor, sorry, quick question.
Okay.
So when we looked at the spheres, I think you're talking about the spheres in the first slide, when we break it up using, let's say, it's distributed on the surface, using surface density, and we find the force, like force acting on another point charge, and we break it up and we find it. Do we just find it's just Coulomb's law? Is that why it works in the sphere?
Yeah. So if the volume is just the sphere, let's say, if that would be volume of the charge, then you can treat entire charge in that volume as if entire charge is at the center of the sphere. And this is only correct for the sphere. Remember, not on an arbitrary shape, on this for the sphere. Now, to prove it, as I've mentioned previously, I will maybe prove to you that this is correct. So in this case, yes, when the charge is spherically distributed, you can just, if the charge is uniformly distributed, you can treat entire charge of the sphere as if it is located at the center of the sphere, and then you take the distance from the center of the sphere. Okay, and then you don't have to really deal with this. But if we will also deal with situation when the charge is not uniformly distributed. If the charge is not uniformly distributed, that will require some integrations, and no, that will be done in the future. But to answer your question directly, yes, if the charge has spherical shape, then you don't have to, you can just use Coulomb's law right away. Okay, but if the charge does not have spherical distribution, then of course that will require integration, as you will see on the next few slides. Yeah, so this was just introduction. I just wanted to introduce that concept of the charge density, which of course was done in physics 1801 as well, but because I will be using these charge densities so very often, so I decided to review that concept. So let me now go to the next slide, and the next slide is the example to calculate the force acting on that charge Q0 due to a very thin rod on which charge is uniformly distributed. So let's say we have that charge on the rod, very thin rod. The charge is uniformly distributed on the rod. For now, you can imagine that this is just a line of charge. Let's say maybe the charge embedded in the plastic. So this is not a metal rod. Okay, imagine that this is just a plastic and the charge is kind of on that plastic. And the linear charge density is given. So that lambda, which is given, that's the linear charge density on that rod of that charge. And we are also told the magnitude of that charge Q0, that's also given. And the length of the rod L is given. And we are also told that Q0 is a distance Y from the center of the rod. And Q0 is actually located on that perpendicular bisector of the rod. So this is the middle of the rod. And Q0 is just now away from the center of the rod. So this I designated as y-axis, which is perpendicular to the rod. So this is 90 degrees. And that distance from the center of the rod to charge Q0 is designated y. Y is given. Y is not variable in this example. Please remember, y is given is just a distance from the charge Q0 to the center of the rod. Okay, and the total charge on the rod is Q. Total charge on the rod is Q, which means that lambda charge density we could also write as the total charge on the rod by the total length of the rod. That would be the meaning of lambda. Q is the total charge on the rod divided by total length. That would be lambda, right? So here is too much information is given because I'm telling you that Q is given and L is given at the same time lambda is given. So, but lambda of course is Q divided by L. So this is given information. And the question is to find the total force exerted by the rod on that charge Q0. And we will solve this question parametrically. So remember that these given quantities are Q0, Q, lambda, L, and Y. These are given quantities, and we will find solution in terms of these given quantities, right? So I'm not giving you specific values of Q0 or lambda or something like this. We will do like now in second year courses, most questions are solved parametrically, kind of a more general and more elegant way than with specific values. So always remember what is given, and we have to find the answer, the total force in terms of these given quantities. So we will do it, like as I'm saying, parametrically. So how to proceed? So you see what I have done, and remember, so please, if anything is unclear, please unmute yourself and ask questions right away. I think that would be the most effective way for me to teach and for you to learn. So when doing these type of questions, you will have to follow really certain procedure. And one part of this procedure is this, that because this charge is distributed on the rod, right, is not a point charge, is distributed on the rod, then you have to divide the rod into many chunks, many little elements. One element is designated. And what is important to do that this should be this element, which has charge, let's say dq, is, you see, I selected not in the middle of the rod, not at the end of the rod, but in arbitrary position. So that element dq, you select in arbitrary position, because when you do it, that will help you to reveal different relations between different variables. Okay, so don't select dq now, it's now in the middle or at the ends, just maybe at arbitrary position. So if this amount of charge on that element is dq, then the force exerted on Q0 due to that one element, we will designate by letter df. Why df? And I designate this df because if dq is tiny, and remember dq should approach 0, right? Because that's differential amount of charge. We should make that element as tiny as possible, right? As tiny as needed, so that we can treat dq as a point charge. So then if it is very tiny, then we can treat this as a point charge. And then the force exerted on Q0 due to that tiny charge dq, that force will be also tiny. So I designate this as df, as differential force. So if dq approach 0, then the amount of force will approach 0 as well. Like it will be very tiny. It will be very tiny. It will not be 0, but it will be very tiny. That's what I want to say. It will not be equal to 0, but it will be very tiny. So that's why we call it df. And the amount of that force df, which will be in this direction, remember df is along the line connecting that charge dq to Q0. And because the charge on the rod is positive and this Q0 is also positive, which I forgot to mention. So Q0 will be repelled by that charge dq in this direction. And the amount of the charge will be equal Coulomb constant K, right, which is equal 1 over, remember that K is 1 over 4 pi epsilon 0. And the product of two charges, Q0 times dq, divided by square of the distance between these charges. So this is the distance, you see that this is the R. This is R. And then instead of dq, I can express dq in terms of that charge density. But another little trick in this type of question is that in this case here, I did not designate the length of that element dl, by I designated here this as dz. Why I designated this dz, not dl? Because you see, step by step, okay, just don't worry, everything will be explained. Because when doing all these calculations, we will have to do calculations in certain coordinate axis system. And this horizontal is designated, this is the y-axis, not x, but y-axis. Z is vertically up, and x is out of the screen of the computer. This is x. So because this distance from that chunk of charge to the origin is given by coordinate z, then it is, we designate this the length of that charge dz. Why? Because if I select different charge, different chunk, let's say at different distance s, z, then z will be changing, you see. For different element of the rod, z will be changing. For that reason, z is of course variable, because charge will be, we have to integrate over entire rod. So for that reason, I designate this dz, because that dz is related to the variable z. When chunk is different location, z will be changing, and z is the variable. So for that reason, the length of this is called dz, not dl, because I don't want to introduce additional variable dl. So I'm not sure if this is very clear. So if you have any questions at this point, yeah, please go ahead.
Sir, I have a question. You can go ahead.
Okay, so what happens when your point charge is below the origin? Does it affect anything?
If I didn't catch your first part of your question because of the disturbance. So could you repeat your question?
Your point charge, where Z will be between the origin and the selected points. What if the point charge is below the origin?
Yeah, that's a very good question, because this rod has final length, capital L. And I answer your question in a minute. So as you will see, a very simple case is when Q0 is just a distance from the center of the rod. But if Q0 would be somewhere here, and that's your question, if Q0 would be somewhere here, then the procedure to solve the question would be the same as you will see on the next slide, but it will be slightly more complicated. You will see that the limits of integration will be different. The final direction, as you will see, the final direction of the force on Q0, when it is located on the y-axis, will be along the y-axis. But if Q0 would be somewhere here, the total force due to the rod will be maybe somewhere in this direction.
How about DQ?
So integration will be more complicated, and it actually, when the charge is a little below that y-axis or above, the question is slightly more complicated, but still the procedure will be the same.
Okay, how about DQ? That's what I asked.
Well, DQ, you can select, if Q0 is somewhere here, you can select DQ again at some arbitrary position. It could be at this position, but then this would be the distance R, right, between DQ and Q0. And you would have to find some relations between this R, between DQ and different angles. So that will be a little bit more complicated, but you should not select DQ, let's say, just opposite to this DQ, because that would not allow you to reveal relationships between different variables. But your question is very good, that this charge Q0 could be at any location, could be above y-axis or below, and that makes the question slightly more complicated. but not overly complicated. Okay, but the procedure will be still the same, as you will see. I on purpose selected Q0, like in the textbook, on that perpendicular bisector, because as you will see, once we find the solution, we will generalize solution for the case when the rod is infinitely long, and so on. So, and for that reason, that Q0 is selected on that perpendicular bisector of the rod. But I think in one of the tutorials, we will find the solution when the charge is maybe at different location. Okay, so maybe in one of the tutorials we solved the question when Q0 is not on the perpendicular bisector. But thank you very much for asking that question. That was actually a very good question, which I'm sure is on mind on many students.
Professor, so I was just wondering, when you said that you're not allowed to choose it directly across, why is that? Like, that you can't have it directly across the...
Yeah, it is not, because you see, if I select that chunk, let's say here, then this would be distance r, right? But I know that I have to integrate, I have to use superposition principle, and I have to divide the rod into many infinite number of these little chunks. And if I select this charge somewhere here, then I would not see what is the relation between distance r, between r, let's say if I take chunk of charge here, the r will be different. You see, r will be changing. And to reveal what is the relation between r and z and this angle here, theta, you have to select that chunk at arbitrary position. That will be probably more clear when we try to find relationship between r and z, because remember, when that chunk of charge is selected at different locations on the rod, z will be changing, r will be changing, this angle here will be changing. So there are actually different variables, and you have to integrate over the entire rod, and you will have to select the variable for integration which is the most convenient. And for that reason, because to select that most convenient variable, we will have to find the relationship between many different of these quantities like r, z, and so on. So the short answer to your question is that don't select very specific kind of a chunk, because you will not see then the relationship between the variables. And when I clear this, you see, when I selected this dq here, then if I designate this distance z, this distance r, and let's say this angle theta, then this triangle here allows me to find relationship between r, z, and this angle theta. But if you select angle here, that chunk here, then you don't see that triangle, and you don't see what is the relationship between r, z, and this angle.
Okay, thank you, Professor.
Yeah, you are very welcome. So yeah, as you see, these questions are crucial. Like it was in Physics 1801, I remember, many of you ask excellent questions, because it helps me to teach, actually, to explain many things when you ask questions. So for now, I calculated that differential force in this direction is kq0 dq r squared. And because I designated, as I've explained, the length of this little element dz, because that element is distance z from the origin, then the amount of charge dq, remember on the previous slide, I have written that dq is equal lambda times dl. Remember, that was on the previous slide. But instead of dl, we have written now dz. Okay, and so I substitute, instead of dq, I substitute lambda dz. And then, in addition, I decompose that force dF into y component. And remember that horizontal axis is called y, not x. X is out of the screen. This is x. So this is dy, and this would be dz. This component would be called dz, dfz, I should say, dfz. Okay, and these components you can find from this triangle here. So dfy this component is equal df, and this angle here is designated theta. You see, this angle is theta, so this is also theta adjacent to dfy. So this component of df, I can write df cosine theta. Okay, now the component this dfz, which I didn't write here, but dfz would be equal df, the magnitude of that force, that differential force, times sine of that angle theta. However, if you devote a little bit of time to analyze the situation, then you will see right away that if I select symmetrically located element on that side of the rod, so if this is distance z, and if this element would be distance negative z, right, coordinate of this would be negative z, then this element dq would exert the force in this direction. Oh, it is not nice. In this direction, more or less. And the z component, so this df, is the force due to this element here on that side of the rod, right? Because this would be the distance between these two charges. And the z component of that force would be up, as you see. And the z components will cancel. So for every element in the upper part of the rod, I can always find element in the lower part of the rod such that these z components will cancel. So actually, these z components will cancel, and the resultant component of the force will be along the y direction. So for that reason, I will not be calculating that z component, because by symmetry, because that charge q0 is on that perpendicular bisector of the rod, that upper part of the rod and lower part of the rod will cancel z components. But you see, y component due to this chunk in this direction, and y component due to this chunk, which is in this direction, y components will add. See, because they are in the same y direction. So I will be calculating only y component, df cosine theta. And because df is given by this expression, I substituted for df. See, I substituted, and I got that dfy is equal, given by this expression, k q0 lambda dz divided by r squared cosine theta. Okay, so this is the first part that we found the component of that differential force df along y component, and now I would have to find, and remember, this is that dfy is only due to one element of the rod, and now I have to use superposition principle to find the total force due to all elements. And on the next slide, we will do that summation, which is really integration, because so remember that, so this is that expression which I have rewritten, which was from the previous slide, that element dfy, this component, you see this component is given by this expression, and this is the force only due to one element. But now I have to use superposition principle. Now I would have to take another element of the rod, right? All elements of the rod, divide the rod into infinite number of little elements, find that component due to each element, and find the sum. But as you know, summation is really integration, because you all took calculus 1014, so you should know that integral really the sum over tiny elements becomes integral, right? The summation of all these forces due to each element will give me that will lead to integration. So yes, so what I have to do, I have to now integrate, right? I have to integrate this expression to find the total force due to entire rod. I have to integrate, you see, this expression, integrate. The problem is that when I integrate this expression, here I have three variables, because as I've mentioned, for different element, z will be different, distance r will be different, and this angle theta will be different. So there are three variables, z, theta, and r. And the best way to continue with this situation is to express all three variables in terms of one single variable, And it's possible to do it because this triangle here, this triangle reveals all that relation between z, r, and angle theta. And as you will see in a minute, actually the most convenient variable to do integration is not z, is not r, is actually this angle theta is the most convenient. To really understand why this angle is the most convenient, please give me a chance to explain a little bit more. Then you will understand why theta is actually the most convenient. Although you could do it because, and the answer in short is that the expression under the integral in terms of theta will be very simple. But if you would like to integrate over z, that integral will be very complicated to integrate. And as you know from calculus 1014, some integrals can be very, very complicated to find the integral depending on the expression. And as you will see, that expression, if we express r and z in terms of theta, then the expression under the integral will be extremely simple. But if you would try to replace theta in terms of z, the expression under the integral would be complicated, and you would have hard time, and you would have to spend a lot of time to integrate over z. And over r would be the same, very complicated if you do. It's possible to integrate over r distances, but the expression under integral is very complicated. So that's the lesson, that when few variables are involved, you have to think hard until you decide which variable is the most convenient to do that integration. And in this case, as you will see in a minute, that angle theta is the most convenient. So now I know it because I did this type of questions before. Actually, we did this type of question in physics 1801 as well, now last year. So it should not be completely new for you. But let us now then try to express z and r in terms of theta. So if this is my goal, then as I've mentioned, I use this triangle, and then express r from this triangle, which is hypotenuse. I can write as y divided by cosine theta. Remember, y is constant, y is given, y is not variable. Okay, so this is one. So instead of r, I can substitute this because y is given, and theta should be my variable. Now for z, you see z is opposite to that angle. So z is equal y tangent theta, right? Because remember that tangent is, no, this is no trivial, but tangent of this angle theta is equal what? Is equal z divided by hypotenuse. So it's equal z divided by hypotenuse, which is r, which means that z is equal, no, tangent, what I'm talking about. Sorry, I better clean it quickly. Yeah, from this triangle, z, the tangent function, of course, tangent is, of course, of that angle is opposite to this angle, which is z, divided by adjacent to that angle, which is y, z divided by y. So from which z is equal y tangent theta. And then, but because in the expression I have dz, I find dz d theta, this integral is, derivative is y divided by cosine square theta, because derivative of tangent is 1 over cosine square theta, which means that dz would be equal this times d theta, right? So this is the expression. So instead of the z, I can substitute this. So if I substitute for r this, for dz this, then I will have only one variable to integrate over, and that will be that variable theta. And that's what I have done. You see, I substituted for r, I substituted for dz, which I did in this step. And then now many things will cancel. See, so here you see that, for example, y we have here we have y squared, so 1y will be left over. Here we have cosine squared theta, here cosine squared theta, so these two cosine squares will cancel. And finally, you can simplify this expression to here, to like this, and you see that there is only now one variable involved because y is constant. And then you have to integrate, and that integration we will do next time, because now time is over. So I have to finish at this point. So I will start next lecture now with this expression, but it's very important for you to go before we meet next time on Monday. Please do some work at home and try to analyze what I was explaining today, so that you are always with me, that you are not staying behind. Okay, it's very important that you come to the next lecture with good understanding of what was done so far. So I will finish at this point, and I will stay to answer your questions, but formally I will stop recording right now, so that recording is not too long. So pause, stop recording. Oh, sorry, I should say stop recording.